let's go for the last talk of the day. Very likely you're a bit tired. I will be talking about the automotive. Why? Because in EPI, we are not targeting only the high-performance segment, but also automotive. Why? Because automotive is a very important segment with increasing performance requirements. Performance requirements in the form of processing large images, detecting objects, being able to fuse data from different sources, and perform intelligent work, for instance, autonomous driving. So let me start putting you a bit in context of what's an automotive system. First of all, just a question. How many of you have heard about ISO 26262? Okay, few. That's okay. Anyway, I will assume that none of you have heard about it because it's a weird thing that people in automotive have. So basically, the idea is that automotive systems are a type of safety critical systems. And they are safety critical systems because a malfunctioning of the system can create injuries in people, in the environment, or just severe equipment damage, okay? So they are critical for this reason. So it's not just like, I don't know, a computer where you have a crash, okay, it bothers you, you reset, you restart, you re-execute, but it's not that bad. If these systems fail, they can kill people. So basically, this has a number of implications that start before even designing the system. When you conceive the idea of, I will put here a braking system in my car, before starting writing a single line of code, you start with a complex process, just assessing what are the risks, the hazards of the system, and then you start coming out with some safety goals that influence on the requirements you have on your design. And then there's let's say, a heavy protocol, because it's a heavy protocol, where these people from the automotive domain start creating tables and diagrams and plenty of information that is quite far from what you usually expect when you are designing a system. And this information is carried out during all the process and influencing the whole process of designing an automotive system. And this has implications from the design, from the architecture specification, implications in the implementation, and then later with the verification and validation of the system until you get the final system. So of course you will have code, and of course you will have the EPI processor below at some point. But it won't be just you plug here a processor and see what happens, but there's a whole set of processes behind. Of course, there are other domains, avionics, railway, each one has its own protocols, but in spirit, they share the same goal. You first need to take into account what you can create, in the sense of what damages you can create, and this determines the level of depth and investment on the design and the verification and validation of your system. So, in the particular case of the automotive domain, we have a number of requirements that are common to other domains, but specifically relevant for automotive. One of them is reliability. You can imagine that your computer may be sitting next to an engine, perhaps operating at 60 or 70 degrees. Very likely you won't have a fan, simply because, I mean, these mechanical components will tend to fail, especially in such a dirty and noisy and just with so much vibrations environment. So it's a very tough environment where components suffer a lot. And they suffer a lot not only from the physical, let's say, dimension. It's not that they are simply hot or they are suffering vibrations, but they are also, for instance, suffering plenty of electromagnetic interference. So you have high voltages just next to your computer. And this is creating errors from time to time, probably much more often than what you may have in your regular computers, okay? Probably the most important aspect, functional safety. This relates to the fact that the malfunction of the system can create damage on humans. And as I told you, this is basically something that has plenty of influence on the design, the verification, and the validation of your system. And in the case of automotive, this is regulated mostly in one standard, that is the one I was mentioning before, is 026262. So if you try someday to open this book, I mean, very likely the second thing you will do will be closing it immediately. It's kind of a legal text that is intended to guide you in the design and the verification and validation of your system. And it's a heavy protocol in that sense. But it must be taken into account, because these are kind of the means that automotive industry use to make sure to gain this confidence on the system being reliable. And finally, security. Security, all of you have heard about security, and the concept of security in automotive is not so much different, okay? So I won't be entering in security aspects in this talk. So the idea is, do we have today CPUs that are compliant with automotive requirements? And the answer obviously is yes. I mean, we have cars outside, and you can guess that most of the cars have between 100, 150 computer systems inside. So you can imagine a car, the size of a car. There are more than 100 computer systems inside your car. And this is real, and this is what we have today. But the thing is that this the performance of these computing systems is relatively low. And this is, let's say, the price to have a design that you can prove that it will operate correctly. And this is a problem. And this is a problem when you move to autonomous driving, where you need huge performance. So the situation is that these systems that we have today, these computer systems, these processors we have behind, do not scale enough for assistance driving systems, for autonomous driving. So we need high performance. And high performance is the performance that will deliver the EPI processor. And that's the reason why we are investigating this EPI processor in the context of automotive, because it's the source of performance needed. However, we have this set of automotive requirements. And this is a hard to comply set of requirements, especially if you take a high performance design that is mostly intended for average performance and let's say for the performance of applications that are not risking lives in general, or at least where a failure is not just killing people. In the case of automotive, a failure can kill people.
Verification process, because of course, security is at stake. I would also assume that you have major issues because you mentioned hundreds of computers in there, and probably not just coming from the car manufacturer, but the vast network of subcontractor suppliers, I guess.
I will get to that.
Okay, yeah. So how do you verify, so maybe you are sure that one of those computer or components is intrinsically safe because you play all the tests, but then when you integrate it together, then it becomes pretty complex. So are you using any kind of formal methods approach or whatever to verify that the entire system, first of all, is safe, secondly, is verifiable, and third is compliant with the necessary norms, standard, and regulations?
So basically, the thing is that in the automotive domain, the process is normally highly evolutionary, never revolutionary. So at some point, they started introducing very few computers in the car. And they verified them, I would say, by brute force, in a sense. Eventually, when the systems started scaling up, they started just making up some tools that help them to perform this verification. And they started building some protocols to do this verification. And this allowed them to keep scaling. And at some point, I mean, the things have been keeping scaling, and the way they've had to manage, to keep, let's say, the time to market within acceptable bounds, and the costs, because costs are very tight in automotive, within acceptable bounds, has been using legacy systems, reusing as much as possible. Just change what you need to change. And in fact, now they are facing the problem that they cannot put more computers in the car. Because whenever they need to incorporate a new feature, the typical thing they do is they add an additional computer. And they have a specific bus system that is already verified, where they know that by connecting the new system, they are not, let's say, impacting the reliability and the safety of the rest of the system. They only need to verify the new system and the point where they integrate. So this is the way they have been working so far.
It's pretty scary. I think my next car will be a Dacia.
I would say, when you learn how verification is done, it's scary.
Yes.
When you see that the engineers doing that verification buy those cars, then you rely on that.
My next car will be a Dacia. Yes.
My question is related to that, but I hope we can also take another approach, which is, let's say that you are trying to work on the self-driven car. Doesn't mean, in my mind, in one model, that we need to control or connect to all the other computers in the system. What I'm trying to say is that if you are trying to deal with other obstacles and things that the car will see, it's not necessary to be controlling the temperature of the engine or whether that independently could stop the car or do something like that. We don't need to control that. The other thing is, you say it's evolutionary, but we will take things as, decisions based on multiple sensors. So there is to simplify the discussion, a majority function or things like that, and only a few signals that are really overwriting everything else. So my thought, and that's what I'm consulting, is that better leave the high performance for the things where you need to process many images and take decisions based on that, and not overload the system with low-level functions that can be self-controlled or are still alive by themselves.
Basically, here is what I was getting. So the idea is that this thing here, let's say the EPI processor, is not ready to take care of a number of safety features, okay? So the idea is that anything that you can keep in your already compliant automotive CPU, you keep it there. But there are a number of new functionalities, performance functionalities, that you will have to offload to this computer. And this is the strategy that will be pursued in EPI, having this kind of master, low performance. In a sense, you can view this like a CPU and a GPU. Okay? But in this case, the CPU is an automotive, reliable controller with low performance, and the GPU, in a sense, is a high-performance processor, the EPI processor, where you will be offloading a number of tasks where you need this very high performance. So just to put you an example of a safety feature that you won't have in the high-performance processor, and that you need to rely on the Oryx processor, for instance, from Infineon. Normally, these systems need two independent clocks. Why? Because you need to be sure that if the system, if the processor has a problem in the clock and gets completely stalled, there's someone noticing and being able to reset the system, okay? This means those two different sources of clock, okay, for the time. Here, for instance, you may have different time domains, but the source for the clock will be one. So the idea is that by having this processor here, this one can be both monitoring the high-performance processor and itself. So you don't need to add this safety feature here because you already have it here. And that's one of the concepts that you get by having this kind of master-slave structure. I mean, this structure, this organization is not new. There are other, let's say, vendors that are trying to go also to reach the automotive market, that are also building on this approach, having a relatively low performance, safety compliant CPU, taking care of all those safety aspects that can be taken care of here, and then the high performance thing where you will add only those features that are really, really mandatory. And that's the idea of what is being also done here in EPI. I mean, it's a good choice, and that's the choice that is being taken. So just let me put you a bit in context of what's ISO 26262, this regulation for automotive systems. Of course, I won't enter into the details, but just to give you an idea, these are some of the main chapters in the book. Each one may be around 100 pages, and they stipulate, for instance, the concept phase. Here you say, I want to do this functionality, a braking system, and I define the main items. And the main items are the driver, a braking pedal, then I have some computer, then I have some communication system, and I have the actuator somewhere. You define just these items. And then you start performing what they call a risk and hazard analysis, just to see what kind of things can go wrong. For instance, I press the pedal, and no signal arrives to my computer. Okay? Just these kind of silly and basic things are the starting point. And from there, they start deriving what they call the functional safety concept. And I won't enter into the details because this is a very painful thing, but at the end, they end up with plenty of tables where they are defining risks, the situations where they can arise, the potential sources for the risks, and a number of informations that are later used when they start the development of the system. Here, basically, you see this V. Probably many of you have seen this V in some other contexts. This stands for the verification and validation process. Typically, what you have is that at some point you have a concept with some requirements that basically come from the safety requirements. And then you start specifying your system, detailing your system. So you start from a big box, and you start splitting into boxes, interfaces, some dynamic views of how the things interact each other, what are the operation modes, what are the error modes that you may have, and you start propagating the safety requirements through all this design as you start getting into, let's say, the low-level elements. And finally, at some point, you enter into the hardware elements, the software elements, where you follow the same process, and you reach at the end, at the bottom, with some specific elements. Here, one of them could be, I need here a computer that needs to run this specific program, and each one of them has specific safety requirements. And here, for instance, there may be part of the system that has no safety, basically because it's doing something that, if it fails, there's another one that is taking care of anything. And then, in that case, you say, okay, since it has no safety requirement, I can use any computer. I don't need even an Oryx or any other automotive CPU. But many of them will have safety requirements. And as you will see a bit later, the EPI processor in some of these systems will have safety requirements. And that's why we are here, because we cannot just take any high-performance processor without any constraint and put it there. And then, of course, when you have the design, then you start with the verification, just to check that the properties you were assuming in your design hold, and with the part on validation where you are testing, testing, and testing. You test your element, you integrate, you test, you integrate, you test, until you get up to the end of the design, and then you are confident that by construction, you are compliant with your safety goals. So the only thing I want you to keep from this is that there's a protocol. This protocol implies having plenty of engineers, expert engineers. Most of them, the main area of expertise is not computing systems, that are able to keep track of all these scenarios, of all these situations, to generate all this documentation, so that at the end, what you get is a reliable car. And this has been done so far successfully, painfully, but successfully, for many cars, for many computing systems inside the cars. And what they find today is that they have to fit these high-performance processors there, which is kind of a big step they have never faced before. And the idea is that we have to provide them with a processor that is able to satisfy their requirements, so that when they reach here and they have a set of requirements for the processor design, they can take the EPI processor and put it there. And this is the work we are carrying out in EPI in the automotive domain. So just to provide you an idea of how to assess how critical is my functionality, and then at the end, how critical it will be the software and hardware components I will have to put there. In automotive, in ISO 26262, they have a number of, let's say, degrees of criticality, in a sense, what they call automotive safety integrity levels, ASIL, where D is the, let's say, the most critical one. So just for you to have an idea, a braking system of a car is ASIL D. Okay, is one of the most critical things. The steering system is also ASIL D. But some others have lower criticality. For instance, the control of the window may be ASIL A. It has some criticality, because if you are driving with plenty of rain and the window opens, you may have some risk. You still can control the car somehow, but it may involve some problems with safety. So it's still with some criticality. And then you have what is called quality managed, which means no safety. Here, it's basically telling you what matters is business. For these ones, there's no safety implication. So you want the system to work well, because if it works badly, I mean, the customer may be a bit unhappy, but you are not killing anyone. So how to size how critical is your system? They basically take into account 3 criteria. The severity of the damage you can create, the exposure, so how much you are exposed to the particular risk, and the controllability you have upon a failure. An easy example, an airbag system. So an airbag system, basically the severity of the airbag by not opening is very high. I mean, it's maybe the difference between surviving and dying. So the severity is very high. The controllability is null. Basically, if in an accident the airbag doesn't open, there's nothing you can do. But however, what they argue in automotive is that the exposure is very low. Why? Because how much time of your life you are having accidents with your car? Very little, okay? So basically, if you have to classify the criticality of your airbag system based on the risk of not opening when you have an accident, they will say very likely that is ASIL A, that you need to verify that much. But the reality is that normally the airbag is classified as ASIL C or D, and because of a different reason. What happens if the airbag opens when you're driving? It may kill you. Not the airbag itself, but it can create an accident that kills you. You are exposed all the time you're driving. And if it opens, there's very little you can do. So basically, this makes the airbag to be ASIL C and D. I know that is a trick example, but just to make you understand what's the logic in the automotive domain to classify the systems. They have to take into account all conditions, all scenarios, whether it opens, it doesn't open, it opens slowly, it's not opening totally, when you're driving fast, when you're driving slow, when you're driving at night, when it's raining, when the car is stopped. So they have to consider all the conditions. They have to do to some extent all the matrix within the conditions to get to what ASIL you are mapped. So it's a whole, I would say, universe what you have behind. But let's get closer to our processor. So let me start with ADAS systems. These ADAS systems stand for the Advanced Driving Assistance Systems. So for instance, the line detector, okay? So the thing is that these systems, by construction, and as most of, as I would say, as all automotive systems today, it has what they call a safe state. This means that, for instance, the lane detector, if it fails, it is enough if it notifies the driver and just shuts down. Then the driver is in charge of controlling that you are inside your lane, okay? You have a safe system, and this means that an unavailable system is a safe system. So basically, they say, my problem of safety now is a problem of availability. Okay, the driver might be unhappy if the system is failing all the time and it doesn't have this lane assistance system. But I'm not putting at risk safety. So in terms of safety, you are done. What does it mean this in terms of the design of my system? Basically, I know that I need to detect that the system is failing and notify the driver. So in this system, where I have my automotive microcontroller and my high-performance EPI processor, I only need the automotive guy to be verifying that the high-performance processor is doing its job well. And if this guy is able to ensure that this one is doing its job, it's OK. If this fails, this detects, notifies, shuts down, and that's it. What are the implications of this? That I need this to be safety compliant, because I need this to be sure to detect the failures and to notify the driver. But for this one, for the EPI processor, in this case, I have no requirement, no safety requirement, just performance that in general makes the system work. However, things change when we go to autonomous driving. Because when we move to autonomous driving, what happens is that we may be at a high speed with the system, with the car controlling itself. And in our car, we won't even have a driving wheel. So no driver, no driving wheel, no nothing. OK? So what happens is that this one is processing images, high-resolution images, detecting objects, and taking decisions on what's the direction to drive. This may detect whether this one fails. But if this one fails, no one is able to detect the objects and keep driving, because this doesn't have enough performance. So basically, it implies that if this one fails, we may have an accident. And this makes that this one has safety requirements. So in this case, this one reaches even the highest safety integrity levels, because it is controlling the braking system, it is controlling the steering. So this is the reason why we need safety support in the EPI processor. Of course, it's difficult to fit this logic, this support, in a processor that is being designed and that has to reach first a given level of performance for the high-performance domain. So the type of work we are conducting is assessing what are the features that are mandatory to be there and make sure that the first design is not against these features. It won't be compliant by construction at the beginning, but it won't be against. So it will be relatively easy to support the automotive segment very soon after the first release. So just a more detailed picture of the system. Basically, we'll have this automotive safe and secure MCU. We'll have one or two EPI processors. Basically, we'll have the microcontroller MCU, the automotive one, just verifying, monitoring that the automotive CPU works well. And it will be managing the devices, the peripherals, as it does in regular systems. And it will be kind of a, let's say, a master for this EPI processor, as I was telling you. Few properties. Of course, here I put two of them, because in automotive, for instance, for the highest integrity level, you need redundancy. It's the only way, physical redundancy, is the only way to guarantee that you are able to survive or at least detect any fault, okay? In fact, it's not only redundancy, but let's keep it here. Let's keep it with redundancy. But if you look at an automotive microcontroller, they have redundancy, but they have a single chip. So they manage everything inside because of efficiency, because of reliability, because of a number of things. So basically, we'll need to provide all these features also inside an EPI processor, a single EPI processor. Good news, by construction, this processor has plenty of cores, it will have multiple accelerators, it's parallel in nature. So we already have the redundancy we need. It's just a matter of mastering this redundancy smartly so that we can deliver the safety we need for our systems. Input-output will be managed by the automotive microcontroller because it has enough power for that. Of course, it will be offloading in the high-performance chip anything that requires a performance level that we cannot deliver with the automotive microcontroller. And finally, it will be monitoring closely that any failure is detected in time and that corrective actions are taken in time. Because something important in the automotive domain is that you don't only need to detect the faults, but you need to do it timely. So for instance, if since the time you press your braking pedal until you start braking effectively, you may elapse, I don't know, 100 milliseconds, this means that if your system has a fault, you need to be able to detect, correct, and brake still within these 100 milliseconds. So this means that this monitor, this microcontroller for the automotive domain that is monitoring the EP processor, needs to monitor at high frequency and be able to detect failures very fast and very soon.
There's one question there.
Yeah.
You have two systems. One may say decision A, the other one may say. One may say one decision, the other one may be against. I have worked on more critical things where you have to have at least 3 options. And so now the decision is taken by the microcontroller. How does it know which one is?
No. I mean, this is already, let's say, a problem that is, I would say, solved in the automotive domain because when they work only with this microcontroller, they typically replicate functions twice for efficiency. What they do is that upon a mismatch, what they do is they reset and re-execute. Because by construction, these systems are verified in a way that you can guarantee that they lack systematic faults. So faults that may appear are random. So they are mostly guaranteed that by resetting and re-executing, execution will be correct. And then this implies that when you design your system, you need to account for the case where you have the fault, you need to reset, you need to re-execute, and eventually you could even have another fault. Or it could be the case that you have a permanent fault that arises again. This is contemplated in the design process. I mean, this design and verification and validation process takes all these things into account. So what I was telling is that what is today taken into account here in the automotive microcontroller needs also to be taken into account in the EP processor. And it will be done. But the ingredients is having this, let's say, physical redundancy inside, and we have it. The good thing is that we have it. We have huge redundancy there. So it will be, in fact, if it was needed to have triple modular redundancy, it can be done. So that's the good thing. So I was moving just to give you a few words on the software side of this platform. I'm not a specialist on the software side, but I will provide you very few hints. The idea is that automotive platforms are not programmed, let's say, as you program your computer. Normally, they build upon a standard also, a specific automotive standard, AUTOSAR, that defines how you design the components, the software components, how they are organized hierarchically into runnables, how you communicate these runnables through shared memory, software components through messages. So it provides kind of a framework of how to design software so that you can integrate software smoothly. And then you can take, let's say, your provide a tier provider with an interface and tell, provide me a software system for my braking system with this interface. And this interface is AUTOSAR compliant. And then you ask for another system that needs to interact with this other. Both are AUTOSAR compliant, they will connect normally. So this already exists, defines all these interfaces, the architecture of the application, some diagnostic mechanisms. And this is what we will still have in the microcontroller, in the automotive microcontroller. And then in the general purpose microcontroller, it turns out that these things are too, let's say, too little flexible to work well. And what industry is already doing, automotive industry, is developing what they call adaptive AUTOSAR. Just to give you an idea, this is allowing applications working on Linux to work on top of this platform. And this implies that the requirements that we may have for the EP processor coming from the software side will be little. And that's a key advantage because this will allow an easy, let's say, reuse of this EPI processor in the automotive domain because it will impose fewer constraints. And just let me put you the challenges we have ahead. I know that I haven't entered into hardware details. The hardware details, you have seen some of them today, and the idea is that we don't want to introduce hardware requirements if they are not absolutely mandatory. So the idea is that we'll have to meet these automotive requirements with the high-performance processor. We'll have to do it, and we will do it. I mean, because this is kind of a tautology in the automotive industry. When they need something, they do it. If they clashes with regulation, with technology, or with whatever, don't worry, they do it, okay? So don't worry, this will be done. This will be working for the automotive domain. Of course, it will be ready for working in, let's say, in scenarios with problems with reliability. A car is not a clean room. A car is not a room where you have air conditioning or where you have, let's say, all the support you need to keep things clean and safe and so on. A car is a dirty thing that vibrates with electronic interference, but still, it will have to work there, and it will do it. Of course, the way to allow the automotive microcontroller to monitor the EPI processor will be basically exploiting two features that are key in many domains: observability and controllability. You will need to control exactly how things are executed in this high-performance processor to make sure that you have the warranties you need for safety, and then you will need to be able to observe that everything progresses as expected, that there are no faults, and if there's any fault, you are able to detect. And of course, the idea is that we'll have to deliver this performance with this processor because no way we have a safe state anymore. At some point, we won't have any driver, we won't have any driving wheel, we won't have anything, and it will be the software running on the EPI processor, the one really controlling the car and taking care of the safety of the whole system. So, of course, the hardware design needs to meet some requirements that are not yet well understood, and we are still designing the hardware. So it's a big challenge, and that's the reason why the European Commission is investing on this. But I can tell you that, I mean, this will be achieved. So I think that's all. I don't know if you have any question. Yes?
About the deep learning algorithms, are they, because I heard that it's difficult to certify them?
It's, I would say, today, certifying deep learning algorithms is not difficult. It's completely against certification processes. There are investigations ongoing. There are already some cases that can be proven to be correct. But let's say the idea is that in automotive systems, they prove, let's say, that the control is correct by construction and that data is within some limits. In neural networks, in practice, what happens is that the control is the data. So basically, this clashes completely with the methodologies in automotive. But at some point, they have some tricks. They have some tricks, and I am quite confident that they will play some tricks that, in fact, they use these tricks to allow some systems not certified to, let's say, be argued that they were certified when they introduce the standard. And this relates to basically to things that are proven in use. So if you have a system that you prove that works well, that works correctly and safely in practice, then at some point you need to provide further evidence than reality. Of course, I mean, this was devised for, let's say, cars that were working, not to clash with the standard, and to be able to reuse the systems of those cars. The good thing that they have today is that what they can do is put an autonomous driving system in a car with a driver, so that they make the system to work and take decisions, but those decisions, let's say, are not, let's say, activating the actuators, but they are recorded. And at some point, you can, after some time, having this system working in millions of cars, you can get this data as evidence of these systems have been working during so many millions of hours correctly. So this is, let's say, a way they will have likely to escape.